All right, welcome to section 11.2. This is on direct variation, and we'll go and start with question number 1 here, and it says, you leave Spokane driving east on I-90 at a constant speed of 75 miles per hour. And I've drawn a little figure over here to illustrate. We have our car, which I guess maybe looks a little bit more like a baby carriage, but I think you get the idea. Heading east on I-90 from Spokane, and I'm going to go ahead and call the distance from Spokane y and our drive time x. And so for part A, we're asked to just complete this table over here. So in the first column, we have some different drive times, and then we're asked to fill out the corresponding distances traveled. So when the time is 0, well, we haven't really done any driving, so we would just be in Spokane at that time. So this would be a distance of 0. After 2 hours, if we're driving 75 miles per hour, right, that would be then 150 miles, right, just 2 times 75. After 4 hours, that would be another 150 miles, so this would bring us to 300 miles there in total. And then after 6 hours, another 150 on top of that would bring us to a distance of 450 miles. Okay. Now moving on to part B, it says as time increases, distance what? Well, we're getting further from Spokane, right? So distance increases as well. As time decreases, distance what? Well, if I reverse that, my distance will go down, so distance here decreases. If the travel time doubles, then the distance traveled, well, doubles, right? Because, for example, if I were to double my travel time from 2 hours to 4 hours, I'm just doubling that distance. So this, I would say, doubles. If the travel time triples, then the distance, well, again, it'll triple, right? If I say triple the time from 2 hours to 6 hours, then I'm tripling that distance from 150 to 450. So we also see a tripling effect here. Okay. If the travel time is halved, then distance traveled is what? Well, that's basically going in reverse of part 3. If I go from 4 down to 2, that's just going to halve that distance. So this distance will also be halved. And then finally, the ratio of the distance traveled to the travel time, well, just to illustrate here, if I took, for example, 150 and divided it by 2, I'm just going to get 75. In other words, the speed of our car. If I took the 300 and I divided it by 4, well, again, I'm going to get 75, right? We're assuming we're driving at a constant speed here of 75 miles per hour. And likewise, finally, with 450 over 6, this is just going to give us 75. So what we're seeing here is that we always get the same value for the ratio. It's always 75, and just for emphasis here, this is miles per hour, right? That's nothing other than the speed of our car. Okay, great. And so now if I go ahead and look at part C, it says, since the ratio of distance traveled to travel time is constant, we say that these two variables are directly proportional. Write an equation that relates the distance and the time and draw its graph. Okay, so as far as the equation goes, well, just going back to what we set up here, right? If I take any distance y from Spokane and I divide it by its corresponding drive time, this is always going to come out to be 75, right? Simply the speed of our car. Okay, now notice here, a slightly different way to write this is to just move this x over and say, all right, y is equal to 75 times x. And what kind of a relationship is this? Well, it's just a linear relationship, right? Going back to y equals mx plus b. Here, right, b would just be 0, and m is 75. That's the slope, right? And that's simply just our speed. Okay, so if I go ahead and say graph this relationship, I'll put the x, the time on the horizontal, and the distance y on the vertical. And I'll just go ahead and label the time here in increments of 2 hours. And I'll label the distance here in increments of 150. And so we're seeing, right, these points here, 0, 0, 2, 150, 4, 300, 6, 450, so on and so forth. So if I go ahead and draw a nice line through these points, right, I'm seeing that nice linear relationship, right? And I'll go ahead and label this with its equation. But again, the thing to take away from this is that given that the ratio of y to x is always the same, right? That's what we're saying here. This really is just describing a nice linear relationship where the y-intercept there is 0. And the slope of this line is nothing other than this speed in this case, okay? So, all right, so now let's go ahead and look at what we're going to call direct variation in more detail, or more generally. We're going to say that two variables y and x vary directly if their ratio is constant, right? So that's exactly what we're just seeing in question number 1. So I'm going to go ahead and write this relationship as y divided by x, so this is their ratio. If this is going to come out to be a constant, so say 75 in this problem, but more generally we'll go ahead and call this constant k, where, by the way, this k is oftentimes called the constant of proportionality. You'll see this term used quite a bit in this section. Okay, that's what this k is, right? And just again to also emphasize, this relationship is really just describing a nice linear relationship, okay, where this is y equals mx plus b, so m here is just whatever that constant happens to be, and b, the y-intercept, is always 0 here. And so if I were to plot this relationship, right, I'm going to get something just like what I saw, okay, in the last example, right? So this would be the relationship y equals kx. The last thing I want to say before we look at more examples, in this graph here, right, just like what we saw with our distance and time, as x increases, y is increasing, and as x decreases, then y is also decreasing. Okay, great. Well, in the next video, we'll look at a lot more examples. Thank you.